Hi, everybody. It My child is singing in the background too. She's listening to
Are you recording your face? I
yep,
want to show him the
this is
singing.
you. So that's my child. She's listening to a pocket radio, and she's listening to Cozy 101 because they're already playing Christmas music. So this is a quick recording on SVD, singular value decomposition. Hopefully you can see the screen. And I just like keep posting this GIF, so that's there. Then one, hope you're doing well. Two, singular value decomposition. It is, um, well, the whole goal here is to just get the idea of what we're doing, um, and then use Python to do that. Then again, keep working hard to find a practice, find a flow, settle in, reach out with any questions. So singular value decomposition. Um, let's work with what we've been doing. So we have, let's look here. So let's take a matrix A. Matrix A is inputted here through Python. It's written down here as -2, -1, -3, and so forth. If we wanted Python to find the eigen values, the EWs, and the eigenvectors, the EVs, then it does that for us. Here's matrix A in yellow. Here is in gray the eigenvalues, and then in pink going across we get the associated eigenvectors. So for eigenvalue 4 we would get eigenvector zero point 0.3, -0.6, -0.7, -0.2. That's not super helpful. So in Wolfram, if you were to ask Wolfram to find the eigenvalues of that matrix, then it lists out your eigenvalues and then it lists out nicer looking eigenvectors. And I'm going to use those in a moment. Then, so here you can see lambda 4 is what I wrote down. Eigenvector 4, 1, 0, -3, 1. It's matched over here, except it listed eigenvalue 2 as 4. There's the associated eigenvector. And to match that with, yeah, somehow there's a scaling going on from up here. When Python ran the code, it said 0.3, -0.6, -0.7, -0.2 is somehow scalable to get 1, 0, -3, 1, or something similar. All right, then what we're doing with singular value decomposition is we're factoring matrices. So here's an idea of a matrix. So take 2, 3, 4, 9, and then just notice it's factorable into this 2 by 2 and this 2 by 2. And this is our whole goal today, is to take a matrix, write it as a factorization of other matrices, and then make sense of what those other matrices are telling you, and then to use part of those matrices to estimate the actual matrix A. So back to matrix A, where we had, again, here was matrix A there. We have our eigenvalues over here and our eigenvectors here. So if we scroll down to a factorization, here we have a factorization for matrix A. We have matrix A on the left. I didn't write it down again. In pink, we have a pink vector or pink matrix times a gray matrix times a blue teal matrix. The pink matrix is a 4 by 4, and it turns out to be the columns are the eigenvectors from matrix A. They pair up by column with the eigenvalues of matrix A. These eigenvalues appear on the main diagonal and zeros everywhere else. So this type of matrix is a diagonal matrix. And then the last, this is the inverse of our pink matrix. And we're writing that out down here. So this factorization, pink, gray, teal, we could refer to it as P, D, P inverse, where P is a matrix where the columns are the eigenvectors of matrix A. D is a diagonal matrix where the entries on the main diagonal are the eigenvalues. And then P inverse is the inverse of matrix P. This specific factorization, P, D, P inverse, only works when the matrices are square. I'm going to scroll down here. The idea with singular value decomposition is that it's going to work for a matrix of any size, specifically non-square matrices. Okay, so let's take this matrix here and let's see. Oh, you know what? I did want to go back up here. This code here was checking that if we had matrix A with its eigenvalues, and then we took matrix P, matrix D, and then here at the end we calculated, this is the calculation of P, D, P inverse. Do we get matrix A again? And I think there's some rounding error there, but we pretty much get A. I'm not exactly sure why we're getting rounding error and not exact, but it's working. You can notice first column, -2, 0, -3, -1. Here we go, -2, 0, -3, -1. All right, yep, back down here. So taking a 4x3, a non-square matrix, and trying to factor it into not a PDP inverse, but some other factorization. We're going to factor it into a matrix U, a matrix sigma, and a matrix V transpose. And let's go talk about what those are, and then we'll look at the code to do that. So the SVD product, this is the components of the product for matrix A are U and sigma and V transpose. These are matrices. It's the singular value decomposition, SVD. The U is a unitary orthonormal matrix. We don't need to know right now what the orthonormal means other than the columns act like eigenvalues for our non-square matrix. Sorry, not eigenvalues, eigenvectors. The sigma is just like matrix D from above, where we have as diagonal a matrix as we can get, and the entries on the main diagonal are what we call singular values of matrix A, which are like eigenvalues for matrix A. And then V transpose, kind of like our inverse for matrix U. So, for example, if we had A decomposed and factored into a matrix U, sigma, and V of t, let's say A was a 4x3, then U would be a 4x4, 4x3 is a sigma, and then on the end, V transpose would be a 3x3. Then, and our takeaway here, nothing we're doing is really cooking up matrix U or sigma or V of t. We're not talking about how to find those things. We're going to use Python to do that. And then once we do that, make sense of that, or make sense of those matrices. This is going to tell you a little more about where those singular values come from. The singular values are the roots of eigenvalues of matrix products, A transpose A or A transpose. The singular values, we're going to refer to those as sigmas, sigma 1, 2, whatever. And they're ordered from greatest to least, then or largest to smallest. And then the rank, that's something to pay attention to. Number of non-zero singular values is the rank of the matrix. So let's go back. All right, so there was our matrix A. We're going to store that into Python. So here's our array for matrix A. We're going to print A, shows up down here. We're telling it to compute U, S, and V transpose. They're all down here. Here's U, here's S, V transpose, here's sigma, and then make sense of those. So A is matrix A. U is what it is. There's not much to say there other than the columns act like eigenvectors for matrix A. Then the takeaway is S. S are the singular values of matrix A. There are 3 of them, and they're non-zero, or there are 3 non-zeros, so the rank of A is 3. Then, if we, whenever we write sigma, sigma would be a diagonal matrix, have zeros in all the entries except for the main diagonal being these teal values here are the sigmas. This was sigma 1, this is sigma 2, sigma 3 that we saw in matrix S, are singular values of A. To check that it worked, if you want to rework or multiply the matrix product, singular value product, matrix U, matrix sigma, V transpose, does it equal A? And it does pretty much. Here you have 1, 2, 5, negative 2, 1, 2, 5, negative 2. We maybe have some rounding error in there, but that's working fine. This next bit of code, it's, here, I'm going to come back to that. So if we scroll down a little further, we're going to find out that if we were to take our product, U and sigma and V transpose, and just take pieces of it. For example, I'll use yellow. So take the first column times the first sigma times the first row. There we go. And not in that order, but that's going to give us an estimate on what A is. So scrolling down, we're saying that matrix A is equal to a sum from 1 to m of a singular value, a number of singular values times a number of columns from matrix U times a number of rows from matrix V transpose. And if we just take one term in our series, then that's taking one singular value, one column from matrix U, one row from matrix V. If we work that out, we would get a singular matrix. It would be the same size as matrix A, and it would be, since we're using one singular value, it would be rank 1, and it would be the best approximation we could get to A using a matrix of rank 1. If we use the first two terms, then we're getting the best approximation to matrix A using a matrix of rank 2, and so forth. So using above, so scroll back real quick. We were up here. No. It was here. So let's say we had some matrix A, and it happened, and our matrix A from above, the one we were dealing with there. The singular values were 8.8, 6.3, and 5.1. So there they are again, 8.8, 6.3, 5.1. If we wanted to find a rank 2 best estimate for matrix A, it would use column U1 and 8.8 and row V1 transpose, and it's going to equal, and then add on to it 6.3, column U2, and then row V2 transpose. That's what we're doing here. So this is about the same as matrix A, and it's the best estimate we can get of a rank 2 matrix using what we know about matrix A. Here's its first singular value, its greatest singular value, 8.8, times, my wife is calling. 1 second. Okay, we're back. Susan was leaving the Y, stopping by the store, and was checking on what to get from the store. Okay, so this was giving us our best rank 2 approximation for matrix A. All right, going back to our code to explain that a little bit. So here we are inputting our 4x3 matrix A. 4x3 matrix A. Here's matrix A. We had, again, matrix U, matrix S, which is listing off the singular values, V transpose, and then sigma, the singular values across the main diagonal, zeros everywhere else. And we checked that. Okay, so now let's check the sum of the left vectors times the singular value times the right vector. This is computing that sum, down here, sum of the singular value, the column for matrix U and the row for matrix V transpose. And what it's doing for us is it's calculating, this code is calculating the difference between our estimating matrix and the actual matrix per the number of singular values we use. So if we were to use one singular value and just take this matrix, sigma 1, U1, V1 transpose, then here we are, and we're off by about, I don't know, a distance of 5, where that distance is the difference between A and A2, this norm distance, and we're calculating it as a 5. As we increase our number of eigen singular values to 2, then, and we had 3 to begin with, I guess, right? Because we had these 3 teal ones. If we just use 2 of them, then we get a more simple matrix, and we get a reconstruction error of almost 0. So it's as though we can build a new matrix based on the 2 singular values and get a matrix that is almost representing the same amount of information as matrix A is representing. That's what that code is doing for you. And here we explain a little more about what that code is doing. Again, our OneNote note is available to you. Our lab for tomorrow runs through these same ideas, and then we can pick up with that again on Friday. If you have questions, please reach out. And as always, hope you all take care of yourself, and I'll see you on Friday.